Hey folks. I had done some of these, but I hadn't got managed to get recording during class, and so I'm gonna go ahead and record these real quick. Hopefully they're helpful. Okay, so this reaction right here, if you play the video, what you'll see is
of the alcohol are required.
There we go. Anyways, this is the important part. You have two of these alcohols. It's under acidic conditions, under heat. And so what's going to end up happening is we're going to get protonation of one of the alcohols, and then that's going to cause that leaving group to leave. And then the other alcohol is going to attack it as the nucleophile. That's then going to have a deprotonation step where the H plus comes off, and that leaves you with the symmetric ether right here. So it's two of these groups, one acting as a acid, making that the H2O plus, and acting as your leaving group. The other one's going to act as your nucleophile.
So produced.
Yeah, right here. That's the H plus right there.
Now the leaving
that.
group is water.
Yep, that's the good leaving group. And then this is that next step.
Along with water.
Where the leaving group leaves and will give us the cation, which is one of those alcohols that's now the cation. That's going to be the electrophile.
Which produces this product.
And then the second alcohol is going to come along and attack that. That will act as the nucleophile in what normally would be called a coordination step if you were to boil that down to its simplest label. Okay, so what we're going to do here is the part A part. We're labeling the different steps of the reaction. The first step of the reaction has to be that protonation. In fact, they have that right there. So the video directly tells you that actually towards the end. Proton transfer, you're protonating the alcohol right there. The next step right there is then going to be heterolysis. That again is actually exactly like the video. And actually, if I go to the very, very end, I can probably get the
watching, and we hope to.
There we go. The closed
Thanks for watching, and we hope to see you.
There we go. Okay. God, the closed captioning is unfortunately placed in that, isn't it? Okay, so the heterolysis step is then the next step right there. And again, that's the leaving group leaving. It leaves with both electrons in the bond, which is heterolysis. The next one is nucleophilic attack. This is labeled here as coordination, which can be a little bit confusing. But the easier way to think about that is it's an SN style attack. It's a nucleophilic attack. If you remember back in the elementary steps we did, that had been labeled nucleophilic attack in those elementary steps. It's also a coordination, that's also true, and it's the second part to the SN1 reaction. This is the SN1 reaction right here. Then the next step is going to be a deprotonation, where we're losing the proton that's right here. And so we lose that proton. In this case, the one that's going to take the proton on is an OH. You may notice, by the way, there's kind of a neat thing about this reaction, is it actually regenerates this reactive species right here. So this reaction can go very nicely. And in fact, acid is being used as a catalyst here. Okay, so again, the next step is actually going to be where we label what roles the alcohol plays. This is the alcohol right here. And so right here, it actually acts as a base. This is our acid, right? It does not act as a catalyst. We never regenerate the alcohol here. In fact, we use up quite a few alcohols in this process. Technically, we use up 3 in this process because we actually protonate one of these alcohols to go ahead and go on to the next step of this reaction. So, we never act as a catalyst in this reaction. We never regenerate the alcohol. We actually generate the good leaving group here, the H2O plus. And then the next one, an acid. The alcohol never acts as an acid. We never lose a proton off the alcohol. The only place we lose a proton in is over here. By the way, that acts as a base again. And that's the ether that's acting as an acid right there. So the alcohol actually acts as an acid twice. in this single reaction right here. Where I said base, nucleophile, it acts as nucleophile right here actually. That's that nucleophilic attack. And that's the nucleo, the positive right there. Notice that's the electrophile right there, which is not the alcohol. And it is the source of the electrophile, that is true. So the alcohol ultimately does make the electrophile, which is right here. So it is the source of the electrophile right there. Okay, that does that. And then next part, we're going to go ahead and draw on our arrows for this reaction. And so the first step of this reaction, notice this is again the same reaction as up here. The only difference is instead of having a ring, we just have a propane here. Or I should say an isopropyl alcohol. Okay, and so the alcohol, the first step of this is we're going to go ahead and use the sulfuric acid. We're going to protonate the alcohol. That's going to generate that H2O plus for the next step. And so we go ahead and move electrons from the alcohol into a bond with the hydrogen. The hydrogen leaves its electrons behind onto the sulfuric acid. The next step then is going to involve the sulfuric acid is still hanging around, it's still there, because we just completed the previous step, right? It hasn't had time to go away yet. And so it has the negative charge on there. Nothing has to be done with that negative charge. That's fine as is. It's a stable conjugate base for a strong acid. And so this right here is then going to be the H2O plus that we generated. Notice that we've actually gained a negative charge on the conjugate base of the sulfuric acid. And we've gained a positive charge on the alcohol, what used to be the alcohol, which is now H2O plus. Okay, so the next step is the heterolysis step. We go ahead and break that bond, and it leaves as the great leaving group, which is water. This is going to leave a positive cation right here on this secondary carbon right there, the one in the middle. And so we go to the next step. We go ahead and represent that. So at this point, we have water that's been generated. We have our cation, which has been generated right there from the previous step. So these are both the products from the previous step. And then this right here is another one of those alcohols. Just like the reaction all the way at the above, we're going to bring in another alcohol, and that's going to act as our attacking species. And so we bring in another one of these isopropyl alcohols, and this is going to act as our nucleophile attacking, and it's a coordination bond. We take 2 electrons from here, and we form the new single bond that will be formed right here with this carbocation. And so the next step then, we write out our product. Notice we'll have 2 of these isopropyl groups bonded to this oxygen, like an ether, but it still has the proton on it. And so we'll have these isopropyls on both sides of the oxygen bonded to it. This will now have a positive charge because it has 3 bonds to an oxygen. And this is going to only have 1 lone pair. So the next step is another alcohol has to come along, and this has to go ahead and deprotonate this ether so that we have our final ether product. This is the portion where we're going to do the deprotonation. That's that ending cap for most of these acid-based reactions. Okay, so the electrons on the isopropyl alcohol here is going to go into a bond. This is that normal acid-base reaction, this being our acid, this being our base. And so that's going to deprotonate. Electrons go into a bond with hydrogen. Hydrogen leads the electrons behind, which will end up making this neutral. Okay, so that's the final step we need to represent. Now please note that you do need to get rid of these products that are not important in the next step. For example, this one was a product from the previous step here, still there, but it's not important. We don't need it for the next step after that, so we get rid of it. This is going to give us the water and the propyl group with the carbocation. We'll need the new alcohol in to do the reaction, and so we have to put that in there. These give us this product right here, and we have another alcohol that comes along and acts as the base. And so we'll have 2 products in this next step. we'll have the protonated alcohol right here, which actually looks just like that, because it actually is that, and the reaction can go forward from there again. And we'll have this one without a positive charge and a hydrogen on it. It acted as an acid, so it's now the conjugate base of that. And so we have two lone pairs of electrons. We have our nice isopropyl ether. And over here we have the H2O plus version of that alcohol. Okay. Let me know if that helps, if that makes sense, or if you have any other questions from that.